Hello. Today I'm going to solve an example where I'm talking about instantaneous center of rotation particularly, but we're going to use all the equations we developed for rigid body in plane. So the first, so we have this rigid body, and we have the velocity vectors at 2 points, A and B, and we're being asked to determine or to find the instantaneous center of rotation. So this is instantaneous center of rotation. And then once we find instantaneous center of rotation, we are being asked to show that the position vector of C, the point we find as instantaneous center of rotation, is equal to the position of A, or A, plus omega cross VA over omega squared. When we drop the under arrow, we said that shows the magnitude of the vector. Omega squared is the magnitude of omega squared. And then show that the acceleration of the instantaneous center of rotation is 0 if and only if the acceleration of A is equal to this expression. Just to remind you, instantaneous center of rotation is instantaneous center of zero velocity, not necessarily instantaneous center of zero acceleration. We're going to show that to have the acceleration of the C, the instantaneous center of velocity, or instantaneous center of rotation, to have the acceleration of that point equal to 0, we must have this acceleration of A equal to this expression. So note that for this problem, we have placed our origin of frame, reference frame at this point. And we are in XY plane. So alpha or omega dot, the angular acceleration, is alpha k. It only has one component about k hat. Same for omega. It has only one component about k hat. So the first question is determine or find this instantaneous center of rotation, zero velocity or rotation. We said that to determine that or to find that, what we're going to do is we are going to draw two perpendicular lines going through the 2 points A and B, and then the intersection of those two lines is the instantaneous center of rotation, meaning that if I draw this line here, and then if I draw a line here, and both lines are perpendicular to VA and VB, this is point C, or instantaneous center of rotation. And then once we find instantaneous center of rotation, we are also being asked to determine or to show this expression is true. So this is my RC. Alright, so we have VA in this expression, so it makes sense to start with the equation for velocity of 2 points in a rigid body. We said that for 2 points, VA, we can relate the velocity of 2 points using this equation. I have VA equal VC plus velocity of A with respect to C. And for a rigid body, so let's write it this way, A with respect to C, this is equal to, this is instantaneous center of rotation or instantaneous center of zero velocity, right? So this term is equal to 0. So we end up only having VA with respect to C. And for a rigid body, VA with respect to C, or velocity of one point with respect to then another point, is always equal to the angular velocity vector omega cross the position of that point with respect to the other point, omega cross RA with respect to C. We have already shown that. You've got to go through the velocity and rotation frame, and then velocity and acceleration in rigid body. There we talked about this equation. All right, so we have omega cross RA with respect to C. Our end goal is to show this relationship is true. So even if you had no idea what to do next, once you look at this relationship, you're going to see that we have omega cross VA. So it makes sense to pre-cross multiply both sides of this equation by omega. So I have omega cross VA equals omega cross RA with respect to C. Right. So the left-hand side is one of the terms we are looking for, omega cross VA. Now, question is how we can simplify, excuse me, how we can simplify the right-hand side. So we have omega cross RA with respect to C. All right. So this is a vector, right? We have done this frequently. When we didn't know how to work with the vector itself, we have separated the magnitude and direction of the vector from each other. So let's first look at the direction of this vector. So if you think about it, omega is out of the plane, and a rigid body is inside this plane. And if you perform this cross product, omega cross RA with respect to C, this is RA with respect to C. So if you cross multiply omega by that, you get a vector which points in this direction. Agreed? And let's call this R prime, some vector. We can call it anything. And then now we want to cross multiply omega by that. So again, omega points out of the plane. So omega, use your right hand rule, and you can see that omega cross R prime points towards point C. So omega cross R prime, use your right hand rule, and you're going to see that it in fact is negative in terms of direction. It is negative RA with respect to C. So this is omega cross R prime. All right, so to determine the direction of this omega, this whole expression, omega cross R prime, we need the direction of RA with respect to C, right? Because once we have the direction of RA with respect to C, we can multiply that by negative sign and get the direction of this vector. And once we have the direction of this vector, because it's in fact easy to determine the magnitude of this vector, we are done, because we are looking for magnitude and direction. All right. So therefore, our next step is to determine the direction of RA with respect to C. Let's call this equation 1 for now. Right. So what we're looking for is the direction of RA with respect to C. So let me ask you this. So how can we determine the unit vector pointing in the same direction of RA with respect to C? This is pretty straightforward. Or E hat, let's call it E hat, is RA with respect to C over the magnitude of RA with respect to C. Again, to remind you, when I'm dropping this under arrow, it is magnitude. All right? So this is what all we are looking for. So let's call this equation 2, in fact. All right, so let's go back to this term on the right hand side. So we have omega, this is extra, excuse me, omega cross RA with respect to C. Right. So whatever the magnitude of this vector is, it should be multiplied but negative e hat so that we can describe the vector, right? So we are separating the magnitude and direction of this vector from each other. All right, so let's look at the magnitude. So the magnitude is pretty straightforward. So we have omega. So right now I'm looking at only the magnitude of this vector. This is the magnitude. So we are looking for omega, the magnitude of omega, and the magnitude of omega cross RA with respect to C. Right. This is equal to, all right, this omega, you can replace it with R prime if that's easier for you to see. You can replace this omega cross RA with respect to C with R prime and then compute the magnitude. All right, so the magnitude of omega is omega, and this is our R prime, right? So what was the direction? So I've already dropped or set sine 90 equal to 1, right? Remember, so I have omega and I have R prime. Omega is pointing out of the plane, but R prime is in the plane. So the angle between the two is 90. Sine 90 is equal to 1. So when you determine the magnitude of a cross product is the magnitude of the first vector, multiplying the magnitude of the second vector, multiplying the sine of the angle, which is equal to 1. Right. So I have omega, and the magnitude of this term now is exactly the same thing. So we have the magnitude of omega, magnitude of RA with respect to C, and then the sine of the angle between the two. What is the sine of the angle between the two, between omega and RA with respect to C? Again, omega points out of the plane, RA with respect to C is in the plane, so the angle between the two is 90, sine 90 is equal to 1. So omega RA with respect to C. So this is going to be equal to omega squared RA with respect to C. So I have determined the magnitude of this expression. So now let's call this 3. All right. Use 2 and 3 in 1, and this is what you get. The left-hand side is the left-hand side. So you have omega cross VA. The right-hand side, now we have the magnitude and direction of the vector. The magnitude was this term, omega squared, RA with respect to C, and our direction was negative E hat. Remember? So that vector, omega cross R prime, was pointing in negative RA with respect to C direction. So we have negative E hat. All right. So what should we do next then? Again, equation 2. So right hand side, again, omega cross VA, left hand side is negative omega squared RA with respect to C. E hat is RA with respect to C over RA with respect to C. So the magnitude of RA with respect to C in the denominator cancels out the magnitude of RA with respect to C in the numerator, and what we end up having is negative omega squared RA with respect to C. What is RA with respect to C? And that should be pretty straightforward. RA with respect to C is RA minus RC, the vector sign. Okay. Right? So, now if you pay close attention, so on the left we have this term. So I'm going to divide through by omega squared. So I have omega cross VA divided by omega squared is equal to negative sign here. So I get minus RA plus RC. So I end up having RC equal to RA plus omega cross VA over omega squared. And that was our end goal. So we have shown that this relationship is true. And this is how we relate with the position vector of C to position vector of A. Right? Agreed? All right. So again, to remind you, we have found the instantaneous center of rotation, and then we have shown that we can relate the position of this instantaneous center of rotation to the position of A using this relationship. Right? And then the last part is show that the acceleration of the instantaneous center of rotation is 0 if and only if the instantaneous if and only if the velocity of point A is equal to this expression. All right, so let me just quickly show how we should do that. It's kind of all right. I don't. Yeah, let's do it this way. Okay. So, all right. So, what should we do? Again, same thing. What we are interested in at the end is the acceleration of point A. Just to remind you, acceleration of point A is, so all I'm doing is going back to your notes, how we related the acceleration of 2 points in a rigid body. The acceleration of point A is equal to acceleration of point C plus omega dot, or alpha, I can use alpha or omega dot cross RA with respect to C plus omega cross VA with respect to C. So this is this equation we derived for a rigid body. So we have related the acceleration of 2 points in a rigid body using this equation. Just again to remind you, this omega dot is alpha. So I can rewrite this in this form. Plus alpha RA with respect to C plus omega cross VA with respect to C. Okay. So, all right, now we have this. What is our next step? That's the question. So, in part A, we have related the position vectors of the 2 points, C and A. And that's what we're going to do. We're going to use the relation between the position vector of the 2 points because, again, we have RA with respect to C. And, again, VA with respect to C is VA minus VC, right? So, again, so what happens here is that we're going to use the fact that the instantaneous center of rotation has 0 velocity and also the relationship we derived in part A. So this is going to be equal to RAC plus, so alpha is our omega dot, so I'm going to write it this way, alpha k hat, and then I'm going to cross multiply that by RA with respect to C, which is essentially negative omega cross VA over omega squared plus omega cross, and then VA with respect to C is VA minus VC. All right, so this is essentially all we're looking for, because now we can simplify these expressions and show that, again, to remind you, the acceleration of instantaneous center of rotation is not equal to 0. Its velocity is equal to 0. That's why it's called instantaneous center of 0 rotation, but the acceleration is not. And we are going to look, so we are looking for the condition under which the acceleration of that point is possibly equal to 0. All right. So to replace RA with respect to C, I have used this relationship which I have shown to be true in part A, and velocity is simply A with respect to C is VA minus VC. And then again, VC is equal to 0. Right? All right. And then, all right, so here I have alpha, I have omega, and I have omega squared. So how can I deal with this? Because remember, again, this problem says that show that acceleration of instantaneous center of rotation is 0 if and only if acceleration of A is equal to this expression. So you already can guess that because you have acceleration of A on the left and acceleration of C is on the right, acceleration of A should be equal to these two terms, right? Because if acceleration of A was equal to these two terms, then AC has got to be equal to 0. Right? Okay. So this one we have already found. Omega cross VA. Now question is, why do we have alpha over omega VA? So, in other words, the question is, how can we simplify omega cross VA? So if you go back to this figure, again, omega points out of the plane, and then omega cross VA is what? All right, so let's do it this way. Let's even expand this and say, all right, so alpha k cross, so I'm going to replace omega because omega is also a vector about k hat. So this is what I'm going to do. Omega magnitude k hat cross VA over omega squared plus omega cross VA. All right. So this should be now pretty obvious, right? Because this omega's magnitude cancels out one of the omegas. So we're already there. So A sub C minus alpha over omega. And now question is this. K hat cross VA. What do we have? So if you look at these terms in the curly bracket, you have k hat. K hat is a unit vector pointing out of the plane. So we're using essentially same type of reasoning that we use here. So we have k hat cross multiply VA. So k hat cross multiply VA, use your right hand rule, it is a vector pointing in this direction. And the good thing in this case is, because the magnitude of k hat is equal to 1, the magnitude of result is always equal to the magnitude of VA. Agreed? Now think about it. So it is a vector pointing in this direction. And then again, use k hat cross this result. So if you do that, you get a vector pointing in an opposite VA direction. Remember, here at the end, we had a vector pointing in opposite RA with respect to C direction. So you should have already guessed that this is a vector pointing in opposite VA direction. And in terms of magnitude, this one is pretty easy because k hat's magnitude is equal to 1. So you don't need to even worry about the magnitude because you already know the magnitude is equal to VA. So it is a vector, same magnitude as VA, pointing in opposite direction. So it is negative VA. All right, so fantastic. So all we need to do here is, I hope it's in the frame. So I get omega cross VA. So this is equal to AC plus alpha VA over omega, alpha VA plus omega, all right, plus omega cross VA, all right, and this is what we're looking for. Because now if the left-hand side, which is AA, is equal to this expression, if this is AA, then AA cancels with AA on the left-hand side, and your AC is going to be equal to 0. All right, this has been a long problem. So I hope that you have learned something, and I hope that all the notes are in the frame. So see you later. Thanks.